Greetings and salutations, I am Ohano the Procedural Barghest. Today I'm going to show you how I made these procedural actuators using geometry nodes. I'm going to try to explain it as fast and concise as I can, but first I'm going to show you the capabilities of my master copy. This master copy has been optimized and cleaned for user accessibility. Its huge list of custom values ensure you won't need to edit the geometry nodes directly. Every setting has been carefully labeled and each has their own tooltip. No manual required. You can pick up this master copy as well as the robot arm on my Patreon. And in this video I'm going to show you guys how to set up these procedural actuators yourselves, minus the pretty node tree. Before I explain anything else, if you guys like this video, go ahead and let me know in the comments. If you have issues setting this up, also let me know. I'll try to get back to those as quickly as I can. Now I'm sure you're thinking, why would we use geometry nodes? Well, my answer is prototyping. I've recently been working on several projects that include robotic designs, and setting up Pistons tends to get cumbersome after the second prototype, or the third, or the fourth. The way you usually make mechanical rigs is great, but it just sucks to keep setting up. You need lots of bones and modifiers to make them work. So what if we just simplify it as much as we can? Well, that's what the node group accomplishes. With just a line and two empties, you have a functional and easily changeable piston or hydraulic. This setup allows me to make quick changes to my designs and test them in real time, something much more time consuming when using the standard method. And since we use pre-made parts as instances, we can swap them out to fit our final product needs. Alright, what about exporting? Exporting still requires the usual bone setup for pistons, so if you want to put this into a game or other software, you still need to set up your rig properly. However, since geometry nodes is a modifier, you can apply it after prototyping to speed up the process. First, eviscerate the cube. Let's first import or create our assets that we're going to use for the actuator. What we need is at least one joint piece, and one piece for the big part of the shaft. We don't really need any other pieces, as the geometry nodes are going to be used to create the actual segmentation part of the actuator. Since I have pre-made assets, I'm just going to import them. Now I'm going to clean up my scene just a little bit. That way I can have a little better layout to show you guys how to do things. First thing we need is at least one point, and we need to create a line from that point. You can create this in many ways, but I actually use the Extra Objects add-on, which comes packaged with Blender. It allows me to just create one vertice, which I can then turn into a line. Now that we have a single line and some models for the parts of our actuators, we can start using geometry nodes. I set up the input and output of our nodes really far apart, so we have space. I'm going to do my best to go fast while giving insight information. First we add a mesh to curve, then a curve to points node. We're going to have to manually set this curve to points node to 1. Plug that curve to points into an instance on points node. Then we instance one of our joint meshes. I'm using a simple bearing joint, but it could be any kind of simple joint really. Could be a ball joint, could be a hinge joint, anything works here. In the output we can now see that the bearing joint is instance on the end of the line. I'm going to go ahead and scale it down, because it's a little too big. Now, we can duplicate these nodes right here. And we can do it again, but this time we're going to add a reverse curve node between the mesh to curve and the curve to points, and plug in the original mesh to curve into the new curved points. And now we have an instance at either end. But now they're not facing the right way. We need one to face one direction towards the center of the line, and the other one to face the other direction towards the center of the line. Luckily, since we are using points, we actually already have that rotational data. So we can just plug the rotation from our points into there. And now they're both facing the right way. The next thing we need to do is instance our actuator shaft, the big round bit that are between the two bearings. To do that, we can duplicate this instance on points node, but not add another curved points node. Now we just grab the object from our scene, plug it into the instance, and plug in the previous curved points node into it. Plug it into the join geometry, and now we have it. I'm going to go ahead and scale a little bit. Scaling it on the X and Y increases the radius. Scaling on the Z increases the length. But now we have the issue of this thing being inside of the bearing joint. That's not right. So if we use a translate instances node, we can go ahead and move it along the Z-axis locally until we like its placement. Don't forget to plug in the rotational data from our curved points node. Now we're getting this weird twisting effect whenever we move it around. The reason for this is that although the line is creating us a Z-axis to follow, we don't have any actual data for the X or Y. So it's just trying to create it without any actual information, which causes this weird twisting effect. So in order to fix this, essentially what we have to do is either find or create data for either the X or the Y, or both. And to do that, we're going to use an empty. We're going to want to create an empty that's directly next to each vertice on our line. I'm going to use an arrow, but you can really use anything. The idea is that we're going to have these instances face towards these arrows. To do that, we're going to have to change our collections a little bit. We need to add a new collection that only has our empties in it. This is very important. Then we're going to add the collection info node into our geometry nodes. It works a lot like object info, except it uses the instances from a collection and not a single object. Make sure you set it to relative and separate children. Now we can plug this to an instances 2 points node. And now as you can see, every instance in that collection has become a point. We can reference that point's position with the geometry proximity node. Plug its position along with a regular position node into a subtract vector math node. Then we're going to get a magical little number called the align Euler to vector. We're going to plug this in. We're going to plug this in between the rotational pins of our curve to points nodes and our instance on points nodes. Make sure that they're connected to the rotation and not the vector on the input. And now you can see that they're pointing in odd direction. That's because they're pointing at the director 0, 0, 1. Now with our previous nodes that we've created here, with geometry proximity, we now have a vector. And if we plug that into this vector in the align to Euler, we'll get the desired effect. You should change your pivot point to Z since that's the axis we know, and change the alignment to either X or Y. In my case, I use Y. The reason that this works is that we're taking the position of the nearest point, and we're taking the position of the nearest instance and subtracting them from each other. The result is essentially a direction. And now as you can see, the nearest instance will always point towards the nearest empty. It does not matter which way the empty is pointing, it'll point towards the empty from its original point. So the arrow is somewhat misleading. And remember, when you actually rig this, you're going to want to parent both that point in the line and the empty to the same bone. Now for the second half of the node group. First, we're going to reroute from the first mesh to curve node. and put in a trim curve node. Set it to length. Set the end meter to something high, like 100 meters. Then we're going to duplicate this and put a reverse curve between them. This will allow us to trim each end of our curve individually. Now we resample this curve, then convert it to a mesh with no profile, then split the edges, then convert it back to a curve. You can set the curve radius right here, and finally convert to mesh with a curve circle for the profile. Now that we've got all this set up, we should be able to create the segmentation, but we're going to need some math nodes. We'll need about 7 math nodes. Set them up like this. First things first, we need a round node. We need to plug that into an add node and set its value to 1. We're then going to plug that add into our resample count. Essentially what this does is this adds one number to our previous input to put into the resample curve, meaning that the minimum that that number can be is 2, which is how many minimum points you need to make a curve. And so any number that we would input later into that round circuit would then be the number of segmentations. Now we're going to need a divide attached to another divide. Set this floating divide to about 100, the other value doesn't matter right now. Plug this divide into a multiply that is also plugged into a subtract, and then plug all that into an add, like this here. Set that add's value to a 1, and now with that, we need to get a little more information. So we're going to use a capture attribute node. We're going to get the spline parameter node. We're going to need 2 of them. Plug the index into the capture attribute and the other index into the subtract that's floating. Then plug the attribute from the capture attribute node into that same subtract. Now we should actually have segmentations, though they might be a little hard to see. This add right here is the minimum radius that our pinion can be. This round is the number of segmentations. The number in this divide is how different each segment is to one another. You're going to want to trim these so that they fit just right between your 2 instances. And there you have it. You have the segmentations done. As you can see, it's working as expected. Keep in mind that it's still trying to point towards the empty that's nearby. Let's quickly fix this little issue right here with the shading. We can make a sort of fake shade smooth using a split edges node, and if we attach it to an edge angle node, convert it to a degree, and then into a greater than, set that threshold to around 30 to 40, and it's going to cut up our mesh only at the very sharp edges. Alright, there we go everyone, that's how you make a procedural actuator. Just as a quick reminder, when you parent this vertex to a bone, you also need to parent this. Depending on if you're having it face the X or Y, it'll either be in front of the bone or it'll be to the side of the bone. If you guys have issues setting this up, go ahead and leave that in the comments section. I will try my best to get to those. If there is any major glitches you find with the system, let me know, and I will do my best to get you guys an update video. Of course, the demo files, the robot arm, the suspension, as well as the entire node group are all on my Patreon. Go check that out if you can. And I hope you guys liked the video, and that's all I have for you today.